Okay, this video is for AP Calculus, and this is going to be the introduction to the unit on infinite series, starting with sequences. Before we get to that, I'm actually going to show you a little introduction thing here. Why would we ever want to study sequences in calculus or infinite series? It's not really intuitive, but you can sometimes represent a function with an infinite series. So let's say, for example, that we have let's say that we have this function over here, f of x is sine of x, which we know has a graph that looks like that. We could approximate that with basically a polynomial, right? The simplest polynomial we could use is just f of x equals x. And that is a perfect representation right at one particular value, right here at x is 0. And it sort of follows the shape of the function curve for a little while, but not for very far, right? Pretty soon, the line is not a very good representation of the function. But if I add another term here, an x cubed term, and I get this coefficient right, then we can actually make the shape follow the function curve for a little further away. And if I add an x to the fifth term, it goes even further out before it starts to kind of deviate. And the more terms I add, the closer this polynomial, this infinite series of terms, which are just powers of x added together with different coefficients, the better that this polynomial or infinite series represents the function that we're attaching to it. Right, so eventually, at the end, really at the second half of this unit, that's what we're going to focus on. We're going to be talking about how we can use an infinite series of terms that have a certain kind of structure to them, added together. A series is a summation of a bunch of terms to represent a function. But in the first half of the unit, we're actually just going to work with the function itself. We're going to talk about the series itself and talk about properties of infinite series themselves. Right, so just keep this in mind for later, that we're moving towards something which is connected to the rest of our calculus stuff. All right, but for now, what we're going to do is take a look at this first topic in the first half of the sequence, or the unit here, which is called sequences. All right, so we're going to define a sequence. What is a sequence? A sequence is technically, it's just a list of numbers in a particular order. Simple as that. List of numbers in a particular order. But it's more formally defined as a function whose domain is the set of positive integers, usually starting at 1, although it can start at other numbers like n is 0. And so you can think of it sort of as this is the input to the function here, which we usually call n. And then there's an output, which is a value at each of those n's. So when n is 1, maybe the output of this sequence is a 5. If n is 2, the output is a 10. 3, the output is a 17, and so on. And then for some sequences, although not all, you can come up with a rule or a pattern that can be used as a function. So you can say there's a function where I can plug in a particular n, and this function will compute the value of the output. So for example, if I were to put this 2 into the function, this would be 2 plus 1, quantity squared plus 1, which is 3 squared is 9 plus 1 is 10, and sure enough, it produces the 10. And if you plug each of these n values in, these values for n, you would get the corresponding output values. So when you find such a function like that, you can label it f of n, a function of n, where n is the input. Or you can more commonly, we call it an, where a is a representation of one of the terms in this sequence, okay? Right, so these individual values here are called terms. So this is the first term. This 10 here is the second term, and so on, the third term. Or if we wanted to label it, we could say this is term A1, A2, A3, A4, and so on. And this n here, this n that's the input, we call that the index of the sequence. So it basically locates how far are we into the sequence. Right, so n is 1 is the first term in the sequence, n is 2 is the second term, and so on. Right. So one thing that we might be asked to do is a problem like this. Write out the first 4 terms of the sequence that's defined by a given rule. So if we have a rule like that, we can write this out. So let me write some values of n here. We want the first 4 terms. So n is 1. Let's plug that in and find the nth term, right? So this first term, which would be called a1, is negative 1 to the, now I'm going to plug in a 1 for that n, 1 minus 1, times 1 over 1 plus 1, 1 plus 1. And so this negative 1 to the 0 power is just a 1, and so this ends up being 1/2. So the first term of this series, which could be labeled A1, or a sub 1 is 1/2. Right? I'll change colors here. The next term of the series would be if we plug in 2. So if we plug in a 2, we would have negative 1 to the 2 minus 1 over 2 over 2 plus 1. Now this is negative 1 to the first power, which is now a negative. So the second term here, a2, which we could label a2, is negative 2/3. Right, so this is just, a sequence is just a list of numbers in a particular order. And since this said to do more, we'll do a third term here. This would be negative 1 to the 3 minus 1 over 3 plus 1, which is now negative 1 squared, which is positive 1, which is now positive 3/4. So I could label this term a3, and the value of the term is 3 over 4. Right? And if I wanted to do one more, n is 4, negative 1 to the 4 minus 1 over 4 plus 1 would give me negative 1 to the third power, which is a negative. So the fourth term, which we could label a4, is going to be a negative, and then it's 4/5. Right? So this sequence has the following. This is the resulting sequence here. 4 terms of the sequence, 4 numbers in a particular order. Okay, so that would be writing out the terms of the sequence given its rule. Right. So more commonly, though, we're interested in what's happening as we proceed to many, many terms, like considering an infinite number of terms. What would happen to the numbers in the sequence? Right. Well, we can say that the terms in the sequence either converge or they diverge. And the difference is that terms that are converging eventually are approaching a single number. So maybe this starts out with an output of negative 1, and then 1, and then 2, and then 2.3, and then 3, and then 4.5. And eventually this is getting closer and closer to 5. So the way we could figure that out is we could take the limiting rule, or the rule for the nth term, and take the limit as the n index that goes to infinity and see if that limit approaches a number. If it approaches the number 5, then we say that this sequence converges to a limit of 5. Right? And it wouldn't have to approach nicely from one side like this. We could have a case like this over here, where maybe it's below a number, and then above a number, and then below a number, and it's kind of oscillating around the number, but it's getting closer and closer to that number. So if we evaluate the limit, we would still get a number for the output. Now, those are all cases where the limit is converging, right? What would it look like if a series it does not converge? We call that diverges. And that would mean if the limit as n approaches infinity of the generating rule goes off to an infinity or a negative infinity like that, then we simply say it diverges. There is no limit. The other way that a sequence can diverge is as you let this go to infinity, we never do actually settle down to any number. So there's no defined limit, because maybe the values of the terms are oscillating, like positive, negative, and they never do actually approach the value. They just oscillate around a value forever. Then we would again just say that that sequence diverges. All right, so one way to determine if a sequence converges or diverges is to graph it as if it were a function and see what happens. So for example, let's say we have that function that we just looked at. We could take a calculator and we could enter that as if it was a function. If this is on a calculator part of a test, we could enter this rule, parentheses, -1, up arrow, variable key -1, and then times the rule is 3 times n. This is a new one, I guess. 3 over, divided by n squared plus 1. Okay. And then I could graph it, or usually what I would do is this. I would go ahead and say, let's go second window to set up our table. And I like to set my independent variable to ask, so that I have to enter a value, and then go second and graph to get to this table here. And then I can type in like 1, 2, 3, 4, and see what output value is coming out. I could enter ones to get a particular term, like the first term here is 1.5, the second one is -1.2, and so on. Or I could go to my second window and set the independent variable to auto, maybe tell it to start at t equals 1, and go up by 1 each time. Then when I do second graph to do the table, I can just scroll down and see what's happening. So it looks like the first term here is a 1.5. The second term's output is -1.2, then 0.9, then -0.7. And if I scroll down, this seems to be, these output values are oscillating around 0, but sure enough, they seem to be getting closer and closer to 0. So if you do have technology available on a test, you can use this to check your understanding. It looks like the sequence does appear to be approaching the limiting value of 0. So we would say this seems to be converging to 0. But we haven't actually proved it. The way we would actually evaluate this to prove it would be to take the limit of the generating rule and see what that limit approaches. And of course, if we didn't have a calculator, we would have to do it this way. So let's say we wanted to evaluate this limit, this right here. Well, the first thing is this part over here, that's the -1 to a power, all that's doing is multiplying by a 1 or a -1. And we already showed that it really doesn't matter if the value is oscillating above or below the value, or if it's just approaching smoothly. We could both say that those are converging to the limit. So I'm actually going to ignore that when I take the limit. I'm just going to take the limit as n approaches infinity of the rule, disregarding the sign, n squared plus 1. Now, if you're being really formal, you could go through all the formal College Board process of this, which would be to take the limit as n approaches infinity of the numerator and show that that's infinity, take the limit as n approaches infinity of the denominator and show that that's infinity, and say because we have an indeterminate form, we can use L'Hopital's rule. And then that means we have the same limit, n approaching infinity, but this time we replace the numerator with its derivative, and we replace the denominator with its derivative. And now we have a constant over a value that's getting really large. So this limit evaluates to 0. Now we have conclusively shown that this sequence is approaching 0, and therefore it converges to the value of a 0. All right. Okay, a couple more examples. Let's do this one. Does this sequence converge, and if so, to what value? The way I would do this is with a limit. Let's do this really quickly. Now, if I'm taking the limit as n approaches infinity of this structure, 5n squared plus 3n over 2n squared minus n plus 4, the point of this problem is not to evaluate the limit, it's to evaluate this sequence and determine convergence. So even College Board is okay with us using other ways to evaluate the limit instead of doing all the formal steps for L'Hopital's rule. You could just note that the degree on the top and bottom are the same, and therefore this limit approaches the ratio of the two leading coefficients. So since that does approach a number, we would say that this sequence converges, and it converges to the value 5/2. All right. Here's another example. Let's say we wanted to find this one. Now this one, we would have to take the limit as n approaches infinity of the rule, n factorial over n plus 1 factorial, right? Now this n factorial is going to go off to an infinity, and the numerator and the denominator is going to as well. But we could just do some factoring here and say that if we wanted to take the denominator, we could peel off the top number in that factorial, and that would leave the rest of the factorial there, which means you could factor out and cancel the n factorial, and that is equal to the limit as n approaches infinity of 1 over n plus 1. And then that means that since you have a constant over an infinity, that limit, sure enough, is also 0. So this series does converge, and it converges to 0. Okay. All right, so taking a limit of an expression for a series as n approaches infinity allows you to determine whether or not the series converges or diverges. Okay, some properties to know about limits apply also to sequences. Since we're using limits to evaluate sequences, we know that if you have a limit, just a reminder from earlier in the course, and you have a constant times a rule, then you can take the limit, the constant outside, and evaluate the limit and remultiply the constant. We also know that if you have multiple rules that are added or subtracted, you can apply the limits separately. So you can take the limit of this rule as n approaches, say, infinity, and separately the limit as n approaches infinity. And then you can recombine these with plus or minus, whichever one that is. That's legal. Also, if you have two rules that are multiplied, you don't have to do something like a product rule. You can just take the limit of this rule, an, and take the limit of the other rule, bn, and just multiply the results. So we don't have to do something fancy like the derivative product rule. Same thing for quotients. So when we do evaluations with limits, it's good to remember the properties. All right, a couple other things to know. We've stated this kind of intuitively, but it is actually a formal property of limits here. if you have a limit as n approaches infinity of an absolute value of a function, in other words, if I disregard the sign, this is what happens if you drop the term like this, where you're disregarding this sign and just making it positive for sure. So if that approaches zero, then that means that the limit with the sign included also approaches zero. That makes sense intuitively, right? The fact that this oscillates around zero, as long as the values are getting small, as n is approaching infinity, it doesn't really matter if they're positive or negative, the limit will converge. And then although we rarely see this, the squeeze theorem also can be applied. If you have a limit that's difficult to find, but you can show that the target sequence has a sequence that's always below and a sequence that's always above that. So for example, you have these terms that are always above and these terms that are always below the sequence that you're interested in, these red dots here. Then if you can show that the sequence above converges to a number, say 6, and the sequence below converges to a number, say 6, if they converge to the same number, then by the squeeze theorem, the sequence in between also converges to that same value 6. So we don't use that a lot, but it's good to know that that's available in our toolkit if we were to need it. Okay, and then there's one other theorem that we are going to include in the homework here. If we just want to know whether a sequence converges, but we don't necessarily need to know the limiting value, then we can apply this theorem. A sequence is defined as monotonic if its terms are non-decreasing or non-increasing, meaning they're only going in the same direction. So a non-decreasing function is basically an increasing function, except that it allows the terms to be the same or higher. They just can never go down. A non-increasing function is basically a decreasing function. It's not increasing. But it allows this case where maybe the term is the same and then continues down. It's just never going in the up direction, right? So if the function is basically increasing or decreasing, but not both, then we can say the function is monotonic. And then there's this rule that says a sequence is considered bounded above if there is a number such that all the terms in the series are below that number. And it's considered bounded above if there is a number such that all the terms of the series are above some number. And it's considered bounded when it's bounded both above and below. So if the series terms are below some value and above some other value, then that means there's a floor and a ceiling that you never go above or below, and that we call that series bounded. So the theorem that's useful for sequences, if a sequence can be shown to be both bounded and monotonic, then it automatically does converge, although this theorem doesn't say to what value it converges to. Okay, so here's an example of that. Let me show you this on another screen. So we've got 3n over n plus 2. Okay, if I have a generating series 3n over n plus 2, what we could do is first of all, determine whether or not the series is monotonic. Is the series monotonic? Okay, to determine that, I'm going to use the derivative. So if I were to take this and write it as a function, 3n over n plus 2, we could find the derivative of this function by the quotient rule. So that's going to be low d high minus high d low over low squared, which is going to end up being 3n plus 6 minus 3n over n plus 2 squared, which is 6 over n plus 2 squared. Okay, and this 6 on the top is positive, and the denominator, no matter what n is positive because it's squared. A positive divided by positive is always positive. Since the derivative is positive, that means this function is increasing, which means it's non-decreasing, which means it is monotonic. So by using the derivative, we can show that this particular sequence's function is monotonic. Okay, and then that means that if it's monotonic and increasing, the terms of this sequence in general are going up. They could potentially go the same, right? Go up. In fact, I think we showed it with positive, so this would always be going up. And that means that whatever the first term is of the series, that's going to be the lower bound. So the lower bound of this is going to be whatever the first term is, A1. which is 3 times 1 over 1 plus 2, which is 3 over 3, which is 1. So there is a lower bound. There is a lower bound. To find the upper bound, we have to see what happens as n goes to infinity. Does this keep going forever and go up, or does it settle down to a number? We're really not sure. So to find the upper bound of this sequence, what we'll do is take the limit as n approaches infinity of the rule, 3n over n plus 2, right? And since these are the same degree, this ends up being 3 over 1 or 3, and that means that's the upper bound. The series never goes above that. Therefore, the sequence is also bounded. It's monotonic, and bounded, and therefore converges. Therefore converges. So I would only go to that extra step if they insist, like this problem says, to determine whether the sequence is monotonic and bounded, right? But then we could, if we've done that, we can use that theorem to say, therefore, it also converges. All right, let's talk about finding an expression for the nth term. So how do we get these rules, right? Most of the time they're given in the problem, but not always. They might not be given in the problem, so we would have to figure that out. And there are two standardized rules, arithmetic sequences and geometric sequences that have specific generating rules. An arithmetic sequence is one where you take a starting value, so like say 10, and then you're either adding or subtracting the same value over and over again to go from term to term. So in this case, I'm subtracting 3, subtracting 3, subtracting 3, and we call that -3 the common difference. If you have a rule of that type, the generating rule will be this. It's a formula that you can memorize. A sub n, the nth term, is the first term, and then you're going to add the common difference n minus 1 times. So if you were to start with this one, the first term is 10, right? So an would be 10, and then you would add n minus 1 common differences of -3. So you could write the rule this way, or you could do algebra and get that it's 13 minus 3n. Right, so one way to generate the rule is if you happen to recognize that it's this special type of series called an arithmetic series or sequence. Okay, the other type is called a geometric sequence. And in that case, we're not adding or subtracting a common value, we're multiplying by a common value. In this case, if we're going from 100 to 50 to 25, we're multiplying by a half each time. And then that means that the multiplier, we call that the common ratio. The symbol we give that is usually R. And then the generating function for a geometric type sequence is it's the first term times the common ratio multiplied by that, the first term by that n minus 1 times. So in this case, the first term is 100. The common ratio is 100 is a half, so it'd be 100 times 1/2 to the n minus 1 power. Okay, now if that's true, let's see, the first term would have to be 100. That means that we would actually have to start this series off at n equals 0, right? Because, oh no, that's not right. Yeah, with n minus 1, n equals 1 would be the starting term. Because if you plugged a 1 in here, this would be, so a1 would be 100 times 1/2 to the 1 minus 1, which is 100 times 1/2 to the 0, and anything to the 0 power other than 0 to the 0 is 1. So that gives me the 100. The second term, a2, would be 100 times 1/2 to the 2 minus 1. So that's 100 times a half, which means we get to the 50. Okay? And then if you have a series whose signs are alternating, then you can kind of ignore that sign at first and come up with a rule, and then multiply by either -1 to the n, or -1 to the n minus 1, or you could also use -1 to the n plus 1. And that will cause the terms to alternate. Which one do you pick between this one or this one depends upon if the first term has to be negative or the first term is positive, and where you're starting your index from, 1 or 0. All right. So you can also potentially get something where you have a series of number or sequence of numbers written out, but you don't have an arithmetic or a geometric form, like this one, where you have the sequence 5, 10, 17, 26, and so on. Could we come up with a rule for that? Well, the numbers seem to be going up, not super rapidly, but not that slowly either. So one thing I always do is I start by writing out n below the term. So if we're going to start this n at 1, that would be the first term, the second term, the third term, the fourth term. So just number the terms. And then start playing around with expressions involving n. Like we could try, say, 2n. And that means 1 times 2 would be 2, 2 times 2 would be 4, 3 times 2 would be 6, 4 times 2 would be 8, 5 times 2 would be 10. But those numbers don't seem to be going up quickly enough to match, right? So that's not necessarily a good choice. It turns out that n squared is, though, because 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. And those numbers are very close to the numbers in the sequence. They're just shifted 1, and they're off by 1. So it suggests that what we could do is we could take the n, we can add 1 to move it over to here, square that number, and then we'll get a number that we have to add 1 to get the sequence. And in fact, that rule can be generated as n plus 1 quantity squared plus 1. So these can be either pretty straightforward or really, really hard. And there's no general way to do it other than try to write out n and write out some things involving n and see if you see any patterns that work. All right, so we're going to stop this video here. It's getting a little bit long, but I do have some additional examples. I'll put that in a second video.